Hey, what's up guys? Welcome to Cert Bros. In this video, we're going to be talking about TCP versus UDP. So let's look back through our TCP IP model, which should hopefully look familiar to you by now. When sending data, we start at the top of the model and work our way down. We're going to ignore the application layer as it's largely out of our control and start at the transport layer. The two primary protocols at this layer are TCP and UDP. A network application has to choose how to send its data. That choice comes down to, do I want to send it reliably or do I want to send it unreliably? Both reliable and unreliable have their benefits and drawbacks. First, let's look at TCP, or Transmission Control Protocol. The first thing to understand is when we send data, this file for example, is not sent all as one piece. It's sent in lots of different pieces of data. The receiving computer then collects these pieces, puts them all together, and then spits out the file. And that's fine, but what happens if some of the data we send gets lost along the way? The receiving computer won't be able to put the pieces together, and you'll probably end up with a corrupted file. So this is the reason we need some method to reliably send data, something that can resend and resolve missing or corrupted data. And this is exactly what TCP does. TCP is the most widely chosen option for transmitting data. This is because it can reliably send and receive data. If there is a network blip and some of the segments are lost along the way, TCP can recover them, meaning the user experience shouldn't be compromised with half-loaded websites or corrupted documents. The way TCP can provide such a stable and reliable connection is in three ways. First, it uses acknowledgement numbers. Second, it uses sequence numbers. Third, TCP adds a checksum. But before any of that can happen, first we need to start a reliable connection. TCP does this by using what's called a three-way handshake, and it looks something like this. First, the sending computer sends a message called a SYN, which is short for synchronize. The receiving computer then replies with an ACK message. This is short for acknowledgement. And it also includes a SYN message of its own. So this message is called a SYN-ACK. Lastly, the sending computer acknowledges with an ACK message. Now we have an open TCP connection. A similar process is also followed when closing this connection down. Okay, so the next step is to look at sequence numbers. TCP will assign numbers to segments as they are sent. This way, the receiving device can collect these segments, reorder them correctly, and determine if any segments are missing. The sequence number is just one field in the TCP header. These messages are then acknowledged. It's almost like saying, sending data, and the receiving computer says, got it. Sending data, got it. And so on and so on. The way this works is by using sequence numbers and acknowledgement numbers. So I also mentioned a checksum. The checksum is the result of a simple calculation ran against the data. If the data has been transmitted successfully, the checksum ran on the receiving side should match the checksum ran on the sender's side. If there has been some problems along the way and some bits got messed up, then there will be a checksum mismatch and the segment will be discarded. As we've already seen, a TCP header is added to the application data to create a segment. This is what a TCP header looks like. We have port numbers, which we will cover in another video, the sequence and acknowledgement numbers, and the checksum. For now, there's no need to worry about the other bits of information. Now, unreliable communication comes in the form of UDP, or User Datagram Protocol. UDP has none of the error handling, sequencing, or reliability of TCP. You can think of UDP as a kind of machine gun of data, just firing and firing, not caring if data is lost or not. It has one goal, and that goal is to send data. So why would we ever consider using UDP if it's so unreliable? Well, while TCP offers a great connection and reliability, it all comes at a price of resource and latency. This is great for the most common tasks, such as web browsing, file transfers, etc., where we don't mind the latency issue in return for a stable connection. Where UDP is useful is in situations where we need live, real-time connections. For example, voice calls, video calls, and gaming all need fast, real-time connections. We can't afford latencies in these situations. We can handle a loss of voice data because who really cares about a bit of jitter in a voice call? On the other hand, if we start trying to resend voice data, then this could cause latency and make the call inaudible. So now let's look at a UDP header. As you can see, there is a lot less information here than there is on the TCP header. We only have the port numbers, the length of the data, and a checksum. The small header means less information, but it's lighter and is quicker. Perfect for real-time traffic. That's it for TCP and UDP, two ways to send data for two different purposes. This video is part of our full CCNA course, which can be found in the description, so please feel free to go and check that out. If you liked this video, don't forget to give it a thumbs up, comment, and subscribe. Other than that, I hope this video helped, and thank you for watching.